Okay, so yeah, I'm Neil Farricker from a company called Geolytix. We started off about 7 years ago, 7 or 8 years ago, a little consultancy firm basically of helping clients, specifically retailers, find new stores. Sometimes closing as well with this time. So there's about 35 of us, so that's only about half the team on there at the moment. So Danny is that right there, he's part of it. Yeah, so we basically started just using location planning, using GIS, using all kinds of data, stats, building sales estimation models. I'll just wait for a few more to come in. So what we generally do is create novel data sets and use population data and any kind of demographic data to come up with nice maps and nice stories to tell the CEOs of the companies that we work for. So this is basically what we're doing. We also build, we're experts in spatial modeling. So we're talking gravity models, regression models, analog models, any kind of way of estimating sales figures for stores. And we also create novel data sets for specific projects for this. So such as retail places, retail points, and also social demographic data, which we'll create using clustering methods as well. We're 100% employee owned and obviously zero debt. So what do we actually do? The key thing is really, you can change anything to do with a store. So you can change your staff, you can change your fascia, you can change your products, but what you can't change is your location. Now you can't move it, and it's the most expensive thing you could actually make a decision on. So you have to get that right as a business, and if you don't, you'll probably fail as a business. So we help the clients place these stores in the exact place where they should be to make the most money. Some of our clients, so our client list is about 150-ish, something like that. So all the major clients you can think of generally work with us. So Adidas, for instance, is probably our biggest one at the moment. There's a few others on there that you probably know. Amazon, for instance, doing the data, the warehouses for Amazon is what we do for the entire Europe. Tech stack, so we rely heavily on mapping software. So there's 3 of them on there, ArcMap, QGIS and MapInfo. We use all 3. Because the clients use different ones every single time. Our favorite's QGIS, because it's open source, which everyone should be using. For the database, Postgres, does everyone use Postgres? Yeah, so there's quite a few, and I presume you use PostGIS as well if you're into geography. That's the spatial add-on to PostSQL. All our stuff's in DigitalOcean, so it's all cloud-based. For modeling, so we generally use all these kind of techniques. So we're heavily into Python and TensorFlow at the moment, but most of our code base is in SQL for client applications. So it's easily deployed into their particular systems. And then for deployment, we use Node.js and Zeit now, so we're all serverless. So there's no servers involved whatsoever. If you're used to serverless systems. Yep. So the key question is finding the drive-through locations. How do you do it, basically? When you ask a CEO or any kind of director of property what they actually want us to do, they'll give you a load of questions and a load of answers. But actually, it boils down to one thing, and that's that question there. Find me more successful locations, basically. Now, we could obviously do a robot and drive around and do some kind of Google car thing, really, which we're not going to do. So we want to do it by a desktop, really, and then visiting sites as well. But this is the key thing, really. How do we actually find drive-through locations? So we use 3 methods. Usually, we do a project kickoff, obviously, and we look for drivers we'll try to speculate the sales of the drivers. Which is basically going to be residential population, working population, shoppers, children. It depends on the client, obviously. So if it was like a toy store, you'd be looking at children. Transient trade, and that's the key one for this particular project because it was drive-throughs. So we're actually more interested in the transient trade, which is basically people driving from one place to another and hopefully stopping off at your particular, well, this was for coffee shops. So your particular coffee shop to get a cup of coffee. So after we speculate the sales, the question we have to ask ourselves is, do we have that data, yes or no? Usually it's a no, so that means we have to go and create it somehow. So these are all the, it's usually open source data we use all the time, so things like small level census data, so that's population data generally, so that we use that for the residential effect. Employment numbers we'll create using business addresses and estimates of employment within a particular area. Shopping areas we'll create ourselves by using OSM shops. We'll create some boundaries and scoring methods. Catchments and traffic counts usually are open source, but that's the main problem for this particular project, which I'll describe in a minute. And then after we've created the data, we create some stats on it, and then we'll compare it to sales to see which ones are the actual drivers, and if it actually makes any sense to the model or not, if that's clear. So the main problem we've got is basically the lack of data for this particular project. So for drive-through, so this is for South Korea. So the project was for South Korea, in the entire country. Now these red dots are basically the actual data for traffic count. So this is the government releasing open source data for the number of traffic points going across each of these links. Now the problem is, it doesn't help me to say, for instance, in this particular area, where should I put a particular drive-through, because I've got no data to estimate the number of cars on that particular link. So we come up with a method to try and estimate those particular points. So that means I'm going from this to a model version, which is this, basically. So I'm trying to infill that spatially extra points on that particular map to say, okay, I've now modeled the estimated car flow at this specific point, rather than something like that, which is very sparse, which I can't use in a model, but something like that I can use within a model. So how do we do that? Graph databases. I presume everyone knows graph databases a little bit, or does everyone work with them? No? Okay, that's good. Each of these nodes basically has some information onto it. So in my particular example, it would be traffic points, but it could be population. It could be anything else, really. So graph databases was used in the Panama Papers in particular, where you had articles all linked together. And then the black lines are basically your relationships between your nodes. So it's basically if someone's related to someone, you'll get a link between it. So it's a way of describing families and management systems, and it's used for detection, fraud detection, and also IT maintenance as well. But I'm going to use it in a novel way, because I'm actually going to use it in a geospatial way. And actually, this is going to represent my traffic network, my road network of the particular data set. And I'm going to link that to the actual points of the data set I showed you before, where it's the very sparse points, and then try and infer from that new sites. And open data, obviously. So you always need data. So we use OSM for this, because it gives you the road networks, basically, for the entire South Korea. And I'll show you that in a minute. But between a centrality, sorry, I should go back to, so what we're going to be doing is calculating how important each of these nodes are, and this is what the between a centrality measure is going to be. So every single one of these nodes, we want to kind of give it a score of how important that node is within the network, and that we'll try and infer from that how busy that particular road is. Okay, so this is the measure. So I've just done a little sample. So I've done the equation there, but generally when you flash an equation like that in a conference, people aren't going to know what it is. So I'll just work through the example, how it actually works. So what we actually need to do is look at all the pairwise combinations of the nodes, and then work out what is the shortest path for those particular nodes. So for instance, if we're going to calculate the between a centrality for node 2, for instance, we need to work out the number of shortest paths. Now, 1 to 5 is one path. There's another path here, which is 1, 3 to 5. Now that it both traverses 2 nodes and has 4 relationships. So those 2 things are classed as the shortest path. So that means we have basically 2 paths, and one of those paths actually touches node 2. And that's the key calculation for this particular one. So because it's basically the number of shortest paths between nodes 1 and 5, which touch 2, which is 1 basically, which is the top one, and then the number of shortest paths in total, which is 2 in this case, so we get half. Now that's the first pairwise combination, because that's just looking at node 1 to 5. You need to do that for every single node basically. So if we do 2 to 3, it's just 1, because that's nice and easy. It's just one shortest path, and it actually touches 2 as well, so that's quite easy, so it's just +1. And then we've got 2 to 4 as well, nice and easy, because that is the only shortest path, and it only touches 2 once as well, so that's another 1. So in total, the between the centrality of node 2 is equal to 2.5. Is that clear? Yeah. Now I could do that for the rest of those particular nodes. So 2.5, 5 to 1, 1, and then from that we can start to see that actually node number 3 is the most important within this network, and that's the key element. And we can also say that the node 2 is kind of important, but not quite as important as the rest of them. And I'm going to use this kind of measure to come up with a way of estimating the car flows in places where we're not, basically where I'm trying to infer it. Okay, so that's the basic way of doing it. There's also the weighted graphs as well. So this is where we put weights on those particular relationships. Now, sometimes you want to do this, sometimes you don't. For mine, I had a nice little measure I could use, because OSM put there's distance involved in OSM, and it also has a speed associated with it. So I can automatically calculate the time traversed between the particular nodes, road nodes of the link. So W1 here might be, say, 5 minutes it takes you to drive down that particular road. So I've introduced some weights to it basically, which I can use. And I can also introduce another measure, which is the one-way flag, which is this is now a directed graph, if you've heard of that. So it's basically, so you can have flows from 2 to 1 in this case, but you can't have a flow from 1 to 2. So that affects your shortest path methodology, and also the weights involved as well. And you'd use an algorithm now called either A-star or Dijkstra to calculate your shortest travel methodology. It's a well-known algorithm which you could use. It's basically a drive time system, really. Okay, so so that's all the data, basically. Yeah, you can see that's the entire road network of Seoul, pretty much for one particular city. That's all the OSM data. So you think that's absolutely fine. The problem with this, though, is that we've got over 1 million road links, and it's a massive graph, basically, absolutely huge. So processing that in a normal kind of way you'd fail straight away, because it will take you all year. In fact, if I set it off now, it'll probably be, I'll be dead by the time it finishes. So it's I'm not going to be doing that, basically. You could basically use Neo4j. This is it's a high-level GraphDB, or you could use GraphDB. Has anyone used these two before? You've used these, yeah? Yeah. Now, what we do at Geolytix, we do a different method. We just hire people to write the code for us. So we basically we'll try and hire the best staff we can. So these 3 people have all worked on this project, basically, writing various optimized code for it, especially Christoph here. He's basically he's very good at the machine learning and scaling everything up to a particular solution. I should mention that if anyone wants a job, There's an email there for you. You should email it if you want to or not. So the solution we came up with was this Google Data Cloud Data Proc. So it's all basically online through the cloud services. It's an extremely good system actually for running clustered machines. It's very cheap to run. It holds all the data in particular. So the way it works is obviously you have the master cluster. So this is basically the master that serves everything, and he controls all these particular slaves. Now in Google, there's two types of slaves. What you'll have, which is stable slaves and preemptible slaves. Now the difference between those two is a cost situation. So the most expensive ones to run are stable slaves. They are constant. They'll always work. They're 100% live, and they won't fall over at all. Preemptible slaves are very dodgy. They'll fall over left, right, and centre quite a lot, quite a bit. They will not complete, and they'll die on you. Now, so the question is, why would we bother with these preemptive slaves and just go with a load of stable slaves? And the reason to do with that really is just cost. These guys over here cost about a penny each, tiny amount, something like that, probably even less than that, to be honest. So you can do, say, 50 of these for every one of those particular stables. It's about £1 for a stable one, and about a penny. It's literally 1/100th of the cost of using these. So you probably want to do a mixture of the two and try and optimize it that way. Yep. Okay, so these are the results of after we've run all that particular method. So it takes about half a day to run these type of things. So they're pretty quick. And we can generate this for the entire globe now, basically. So we've got a full global data set because it's all OSM. And it's instantly resellable to all other clients that do drive-throughs. So that's what we try to do as well. We try to make sure that we can try and resell data. So we'll usually make a loss on the first one and then make a profit on the second one, if that makes sense. But this is the results of it. So you can see that every single link is a choropleth map, basically. So the hot ones are the red ones, and you can see it's generally all the motorway types, the A roads, the busy roads you'd expect to see a drive-through, really. And the colder ones are the ones in either on the outskirts or residential areas where it's not having an effect on the graph that much. So is that it? Well, pretty much, but the only issue is if we don't have any actual data to control the model in the first place, so I'm talking the actual raw traffic count data. If we don't have that, we've got an issue because we've got nothing to control to. And this depends on which country you're in, really. So if you're in, say, China, you're not going to get any kind of traffic data whatsoever, or probably any data, actually. But that's a different point. So what do we do instead? It means we have to generate our own traffic points somehow, or some kind of way of grading a particular area. So the way we do that is using TensorFlow and neural nets. So this is basically what we're going to do is train a neural net model to recognize cars on roads, and then we're going to use those cars on roads to actually grade that particular link. And this only works because well, I'll talk about it in a minute, but this only works because we're grading large roads. If it was just normal residential roads, it would fail, which we'll see in a minute why. So the first bit of this is tagging, the painful bit. Now you could use something like ImageNet that stores all the particular images that people have classified. The problem is it's not the use case here because it didn't work that well. So it means we have to do a painful job of actually just tagging several different types of aerial imagery with cars. It's just a painful thing that someone has to do. And then we're gonna train it. So we tried a couple of different models for this, which was a single shot CNN, and we've also done a faster CNN algorithm. So this is the faster one. Right, I presume everyone knows about single shot, where it just looks at the image once and then processes it as it goes along. That's kind of works well. It's fast, but it's not quite accurate enough. Now, a faster CNN works a hell of a lot nicer, but the problem is it's about 3 times as slow. So you have to really try and play around with the two to come up with an optimized way of doing it. But it's basically like a single shot, but it takes a second stage and it adds a regional effect onto it. So it's a more spatially aware type CNN. But it still works quite well. Yeah, so this is the kind of speed impacts you'd see. You could probably optimize it a bit more with the hyperparameters. But this is a single shot training algorithm. So this is how much the loss function decreases over time. So you can see that's hitting about 300 epochs there. Whereas a faster CNN, you can see it's a hell of a lot slower because we're already at 9,000 and it's still a little bit sporadic as well. So I could have run that a bit longer, but I already ran out of time because I didn't want to spend too much time on it, really. And then these are the results, basically. So you can see that the single shot calculation, we're basically missing we're not missing some cars, we're actually misclassifying some particular cars. So it's picking up things like boats and stuff, whereas the faster CNN is basically the one we went for, and it's picking up nearly everything. I'm not too fussed about missing the odd car here or there. It's the way of grading the links that's the most important. Now, how do I use that and actually assign those particular numbers to a link? And I use that using OSM data and a little buffer on the roads. And then all I have to do is work out where those points lie on the particular roads and then just concentrate on the A roads and the motorways. And then that gives me a way of grading a link and to get me a kind of actual data that didn't exist before. And then I can use that within the graph theory and come up with a whole countrywide way of estimating traffic for these drive-throughs. And I think that's about it. I think I've rushed through that a bit. Yeah. What time are we on?
It's okay, we have questions.
Okay.
So, well, we can have a short applause, of course. So, does DigitalOcean work well for you, considering switching to Azure and AWS?
Yeah, so it works well for us at the moment, but we are considering switching to Amazon Cloud or Google. I think it's Google we've decided to go down the route of at the moment. But DigitalOcean at the moment is working quite well for us.
Okay, have you tried using something similar to Google Traffic Information for estimating car flow in cities?
Yes, we have. So the issue with the Google ones is that it just gives you a grade, like a 1 to 10 number. Whereas this actually gives you continuous data. And continuous data is always better within a model. So that's the reason we actually use our model versions rather than any kind of provider's data. It's actually the same with mobile data because they release another data set, but again, it's grading links, so it's more categorical data, and that doesn't help you estimate the sales estimates for a particular coffee shop. Yeah.
Okay. Well, maybe you answered a part of this, and maybe not. How did you match a segment of a road to OSM and on your graph? You are splitting the segments per count or per OSM way?
It's an OSM way, so we use a k-nearest algorithm. N-nearest algorithm will get you exactly the link that particular point is associated with. So
explain a little bit.
It's another. It's basically it's an algorithm written in Postgres actually, where you can just say which is the nearest link to this particular point, and it's an extremely fast algorithm you can use. Yeah, I'd have to write down the equation for you to do it.
How do you map matching the detected objects on the graph?
Postgres is the way we do that. Yeah, all in Postgres.
Okay, and we have the last question is: did you outsource the manual tagging of the cars in the satellite images, or do it in-house?
Yeah, we did it in-house. So we have a good team because we know exactly how painful that is. So we generally split it up between the team, so it's less. That's including the direct as well. We'll actually take, say, 100 images each and then just tag it all within the space of a day. So it's still quick, but it's still painful. What you could do is do a mechanical Turk, if anyone's heard of mechanical Turk. No? Yeah. So mechanical Turk is basically an Amazon initiative where you can post a job on this mechanical Turk, and it could have, this one's a particularly nice one because it would have worked quite well. You ask the community, which is usually people in China or India, can you tag this image? And then you pay them for every single image to tag for about a penny. You actually control the costs. So you say a penny per image. Can you go away and tag it? And you'll get a load of students actually coming to you and actually doing the tagging for you. So it's a great method actually. We should use it more. We're thinking about it.
So
yeah.
In what countries were you, doing your work so far?
Yeah,
I mean, you mentioned Korea.
Yeah. So this is it's global, so we can actually use it anywhere, any particular country. So the countries we operate in at the moment is Japan, Australia, Korea, all of Asia actually, Europe, not America though. We can't crack America yet.
And how long do you need? I mean, how much time do you need to map everything and to come with the solution, with the first answer?
It's usually a couple of weeks, something like
Only?
that. Yeah.
So you get everything from Google. I mean, you get all the.
We source it either ourselves or from OSM. Is usually where we go. Or we've got contacts in the countries where we can actually rely on people to hand us data as well.
So the question again is, if you're doing it in a couple of weeks, there are places where the traffic is a seasonal thing.
Yeah.
I mean, there are tourist places. There are other places where where there's some work in the road, so you have a different input. So how do you deal with that?
Yeah. So we, for instance, with the neural net approach, you'd expect that to equalize over the times of the year, basically. So you can actually take a few images at the same time, and there's historical imagery as well, which you can rely on, and then using an average of those kind of measures, you can actually get to a robust number from that.
So basically, then you get a pretty good model.
Yeah, exactly. Yeah, and then this is just one input to the drive-through models, because that's just your transient trade. You'd be adding on your residential, worker and shopper, and any other kind of models you'd expect to add on to that, really. So this is just literally one element of a model we build.
Neil, thank you for this. May I present you with a certificate?
Sure. Thank you.
For this stuff you can show you. Yes. Thank you.
Cheers.
This is Neil Farricker.